symmetric, right? CG, CG, triple A, CG, CG, but there is a directionality to it because it's coupling from these thiol groups. The thiol is sulfur hydrogenate, so and this thing binds very well to gold. So sulfur really, really likes to bind to gold. So you make a thiol group, it binds very well to the electrodes. That's why they do it. But you see, it's binding from the 3 side and from the 3 side here. So it looks almost palindromic, right? Going from here and going from here, the system is almost perfectly symmetric, except for these A's and T's, right? We all know that A and T like each other and C and G like each other. It's like almost perfectly symmetric. And really what you see is nothing special, right? You see like this kind of ohmic nice behavior and very little rectification. Current going to the left and current going to the right, essentially the same. So Ben-Gurion asked himself, what would happen if I make it even more symmetric, if I exchange these T's with A's? So this is what he did. He took this, this strand and replaced these T with A's. Now, A's and A's don't like each other, right? They like to come in pairs, and A's do not like each other, so they kind of form a bubble. So you, in order to, and if the DNA wire is too short, the bubble will detach the whole thing. So you have to glue it together, and they glue it together with this molecule called coralline. It has some structure in real space, nothing to write home about. And now you see that this molecule looks perfectly symmetric. But this is the current that they measure. And this current shows a rectification ratio of about 15, which is already quite statistically significant. And of course, this is the average over thousands of measurements. So this is just the collection of curves. And this is the statistical average. And it's very, very, very statistically significant, the signification ratio. And you can do it with various measurement techniques. So these dots are different measurement technique, and you still see the same behavior. And if you only do it with the poly-CG films, you do not see any rectification ratio. So this is the control measurement. So it's quite significantly robust. So here's a puzzle for you, right? You make the system more symmetric, and you get rectification. And this is what he was telling me about, and this was a puzzle, and this is where we came in. And we made a model. So this is the model for DNA, right? So this is the DNA structure. Is anybody seeing this double helix for the first time? Probably not, right? Everybody knows this is the structure. But in terms of electronics, we don't care that it's a helix. We just care that it's a ladder, that they come in pairs. So we construct this very simple tight binding model. And actually the tight binding parameters of all the different bases were actually calculated in Tel Aviv by Yonatan and co-workers. So we have all these numbers. And what we take into account is the fact that when you apply a voltage bias, you get this voltage drop. By how much, we don't really know, but for sure you get some voltage drop because we see rectification. So this is the model that we have. I'm not even showing the Hamiltonian, but you can ask me later. It's very, very simple, non-interacting. And the first thing we do is we take the non-treated DNA, where the parameterization should be quite good, and we compare theory to experiment, and essentially we have only 3 parameters. One parameter is the coupling between these thiol groups to the gold. The other parameter is the shift that the bases feel when they are close to the gold electrodes, because you know they're electrostatically gated because there are many electrons in the gold. And the other parameter that we have is how much of the voltage is actually dropping on your molecule. And we also, we even take the gold chemical protection as a free parameter just to make sure that we get the right parameter. Indeed, we get something within the range of 5 to 5.3 electron volts, which is the value for the known value for. Now, once we have these parameters, and you see the fit is, you know, essentially perfect, right? Now, these parameters should not change when you treat DNA, because all you're doing is changing things at the center of the DNA. Nothing is changing at the sides, right? So these parameters should change. And now with these parameters, we can change only the things that happen on the inside. And when we take the inside parameters, the tight binding parameters of the central regions, which are treated with the correlline, this is the fit that we get. And as you see again, the fit is very, very nice, right? Over a large, I mean, the fit is essentially as good as it can get, right? Right, as good as it can get. But the point is that the DNA strand has some symmetries, right? Because these triple A's, they possess some symmetry. And no matter what we tried, in order to get a fit as good as this, we had to break all the symmetries, all the internal symmetries of that region in DNA. And this is the take-home message here, that when you plug in the correlline, you're breaking the internal symmetries that the DNA possesses. And that's why you can get a rectificator. You can get this rectification ratio. And this is kind of how it looks like when the system is not treated. This is what the orbital, the frontier orbitals, if you want, the valence orbitals look like. Right? They're fairly symmetric. There's not much difference between left and right. Now, if you add the correlline, you see that now, and this is just the wave function squared, so this is just the weight of the electronic density on each position on the DNA, you see that there's a very, very large left-right asymmetry. And the thing is that this asymmetry occurs due to the fact that you're changing something only at the center of the DNA. So it has a long-range effect. That's quite nice, quite interesting. And there's another thing to learn from it, and this has to do, this is a delicate point, so if it flies over your head, that's fine. The central change in the current is not to a change in the resonance, but rather to a change in the background current, which means that there's contribution to the current from many, many, many levels in this molecule. And this tells you that this kind of thinking, that you only have one or two orbitals contributing to the transport, doesn't work when you have a complicated molecule. So there are two things that you need to, which were new in the system, and yeah, let me not go into these details here. The third thing I want to point out is that you can actually make a very simple model for DNA, just two levels. And then if you plug it into the machinery of transport, theoretical machinery, you get fairly nice fits. I mean, they're not as good as the one with the full DNA, but they're okay. And this assumes that transport is coherent, right? That when an electron goes into the molecule and then comes out of the molecule, it maintains its phase, its wave function, its quantum coherent. But molecules are typically very floppy and very sensitive and very large, so there's an environment involved. So some people would ask, present included, what happens if the molecule, the electron loses its phase? How do we know if transport is coherent or incoherent? I mean, is this a classical system or is this a quantum system? This is a question that's bugging me a lot. And for this system at least, you can make incoherent calculation. You can actually calculate what would happen if the system would be purely incoherent. And in fact, what you get is something which looks very different from this data, even for the untreated DNA. So at least as far as we can tell from fitting the theory, this to some extent is a coherent problem. Electrons travel here coherently, which is quite amazing, because DNA is a very complicated and very floppy and soft molecule. But still, the fact that you can maintain coherence is quite interesting. Of course, we believe that if you go for longer molecules and longer DNA, and this has also been measured experimentally with various techniques, you will see incoherence come into play. But at least for this system, we believe it's good. So this is the second story, and as I said, it made us very, very happy. Eventually, it made a very nice publication, and it was on various news outlets, and I made it to the Israeli radio even, trying to explain to the general population what a diode is. Turns out, well, I don't know about the general population, but radio hosts are not easily, it's very hard to explain to them what a diode is. At least that specific host. It was a really fun experience for me. So we made the world's smallest diode. And then I went back to Ben-Gurion's group for another discussion. This was a year later. And this is where this first story comes about. And this is a story about photoconductivity. And let me just tell you that you can attach molecular junctions and couple them to light. But it's very, very hard. There are very, very few experiments which can actually do that. And one example is the work from the work in ASU and Taiwan and Negev and people like that. And this hasn't been repeated quite many times. In fact, this hasn't been repeated at all. And this is what they do. They make a molecular junction, and they take these very large, very ugly-looking molecules. I don't know if you can see it. It's quite bright. So this is a buckyball, and it's coupled to a porphyrin, and this is kind of a standard donor acceptor. This is kind of the molecular version of a p-n junction. This likes to give electrons, this likes to take electrons. So this is a real p-n junction, which you would need to make a photodiode, for example, right? And then one of the electrons is ITO. ITO is a conducting glass. So you can shine light through it. They do it, and what they measure is the conductance. So they do many these experiments, so they get a histogram of conductances. And you see this is the distribution of conductance in the dark. Most of them has zero conductance. This is just an empty junction. But some of them have one molecule. And if you look at the conductance under illumination, it's quite different. So something is happening, and that something is called photoconductivity. A change in the conductance when you shine light. Now, it's very small. If you can make photoconductivity, you have to be of the order of 1,000 or 1,000,000, then you could really make a photo switch. And photo switches are very good because photo switches work at the gigahertz and even terahertz regime, while electronics work at the megahertz at most, tens of megahertz. So if you can make photo devices, that's really, really, really. But it's very hard, right? So there are very few examples of this, and there's been a very long and detailed review article, theoretical review article about molecular opto-electronics, and this article was written by Misha Galperin and Abe Nitzan. And Abe Nitzan is really one of the pioneers of the field of molecular electronics. So this is, if you really want to learn something about the theory of these systems, you should really go to Abe's papers and his book. And this was really the lux et veritas of this field. And this is the reason I was really puzzled about the experiments that Ben-Gurion showed me. And I came to see him, and he showed me this experiment, and he said exactly the same thing. You only look at our experiments, you get really large photoconductivity, and my immediate reaction was exactly the same. That's very strange. Your molecules look symmetric. True story. I mean, it was very funny then. It's still funny now. So let me just explain to you what the experiments are. And this is the experiments. He takes the molecule, he puts them in this drawbridge geometry, and because he has this geometry, it's planar, he can shine light from above. So he doesn't need this ITO electron. Still hard experiments. But then, and he takes this molecule. This molecule is called PTCTI, whatever it means in the jargon of chemists. The special thing about this molecule is that there's nothing special about this molecule. It's planar, it's symmetric, it's made of aromatic carbon rings, it's coupled in the edges, nothing special. You shouldn't see something spectacular in it. But then again, when he looks at the distribution of conductances, right? So he does this experiment many times, measures the conductance, and he gets this distribution. Again, there's a huge peak at 0, right? Because 95% of the times you measure no molecule at all. So the yield is about 5%. So 95% of the times you measure nothing. So you get conductance of 0. So we're being honest here and showing you the raw data. And this is the peak where you have a molecule, and this is in the dark, and this is under illumination. And you see that there's a very clear difference between the two. Mind you, the difference is less than 2. It's about 1.6. Not something to rush and write home about. But statistically speaking, it's a very clear difference. And even more so, it's an experimentally clear difference. And by that I mean that if you take two students, have them build the experimental device, and have them measure the same experiments, they can both see it. Right? And if you have two students seeing the same experiment, then that's what I call experimentally real. It's not an artifact, it's real. I mean, what's the origin of this effect is a different story. So why did I say it looks very strange? What? Yeah.
In the previous slide, what's the unit of the x-axis?
Sorry, the units?
The unit of x-axis.
This? 10 to the minus 5 g naughts.
10 to the minus 5.
Yes, oh, yeah. I would, yeah, it's not very good resolution, not sure why. Yes, these are very poorly conducting, really off resonance there. So this is 10 to the minus 5 g naught. It's not a very good resistor, but it might be a very good photo switch, because think about devices, technologically you're going to have many of those. So maybe you will see something. And one thing I forgot to mention, the way he does that, he illuminates light in resonance to the HOMO-LUMO gap. Right? So in semiconductor language, this is illumination in the semiconducting gap. Right? So you're really pumping electrons from the valence to the conduction band. You're really kind of trying to do a photodiode in this sense. Right? So this is what we have. Now we need really to consider both the HOMO and the LUMO, the valence and conduction levels of the molecule. Right? This is the molecule, this is the thing. And what happens? There are two channels now for transport. An electron can hop from the, say, left electron to the LUMO and down, or a hole can go to the HOMO and back, or something like this. So there are two channels for conduction. And in order to understand why asymmetry is essential, it's really, really easy to go, mentally speaking, from the extreme asymmetry case, right? So think about unrealistic asymmetry case where you have the HOMO level only coupled to the left electrode and the LUMO level only coupled to the right electrode. Of course, you can't do that in real life, but that's why these guys from ASU try to use this very ugly asymmetric molecule with this buckyball and porphyrin, because you're trying to separate the couplings of the HOMO and the LUMO as much as you can, right? If this is the situation, then the conductance will be 0 in the dark, right? Because an electron that is trying to hop to the LUMO can't do it. These things are just disconnected. And same thing for the HOMO. It can hop to the HOMO, but then it's not going to be able to go to the other side, just disconnected. So the conductance of this guy is essentially 0, right? But now, if you shine light, then there's a channel for an electron to go from the HOMO to the LUMO. So now an electron can hop into the HOMO, go to the LUMO, and go to the other side, or vice versa. So the photoconductivity of this perfect thing will be infinite. The ratio between the conductances under illumination in the dark will be infinite, right? So this is the most asymmetric case. Now, the more symmetric you make it, the less this effect becomes important. Until when the system is perfectly symmetric, you expect 0 conductivity. So what's the missing ingredient? And this was bugging us for a long time, because we went to the paper by Gadperin and Nitzan, right? The famous review paper, there's nothing there. There's no secret ingredient. And it turns out, at least one mechanism that can do that is the exciton binding energy. That same exciton, or at least similar to what I told you previously. So this is what binding energy is, and in molecular systems this is very important. So think about a two-level system. Right now, go back to your quantum physics 101 theory. You have two levels which you can occupy. So you have the overall 4 levels to the entire system. First, it's unoccupied. Let's call this energy 0, right? Now, when you occupy a single electron at the HOMO level, the system will have some energy, right? This is just the energy of the valence orbital, the HOMO orbital. Or you can occupy the LUMO level. Then it will have some energy, right? I don't know, minus 1.6 electron volts and 3.9 electron volts measured from the Fermi level. Some numbers, right? But if both of them are occupied, you're occupying 2 electrons on a very small space, right? So they're going to repel each other due to the Coulomb interaction. So the energy of this guy is not just the sum of the energy of this and this. There is another term, which is that the Coulomb repulsion between these two. Or you can move this number to here. You can call this number E2 minus U. Right? This is the difference between physicists and chemists. Physicists call this the Coulomb energy, and physicists and chemists will put the U here, give it a negative sign, and call it the exciton binding energy. But it's the same thing. It's just the difference between the sum over these two and this state. And this difference is due to the Coulomb repulsion of electrons. And quite surprisingly, this has never been considered in the literature in the context of photoconductivity, right? And in fact, it can be very large in the gas phase. It's about 2 electron volts, but it's around 0 point something in the junction, because Coulomb effects are screened by the electrons in the electron. And this is a well-known effect. So what happens here? Right? So now, how would this generate photoconductivity? Right? If you have nothing, then you have 2 channels, as I said. One going through the HOMO, one going through the LUMO, and these channels are unaffected by light. The only channel that is affected is the following channel. You go to the HOMO, you go to the LUMO, and you go on. But in reality, if the system is symmetric, that channel is also unaffected by light. The only thing that happens is the following. Let's say you have an electron in the LUMO. Now you shine light, right? You shine light on it, you get an electron to jump from the HOMO to the LUMO, and that electron will sit there for a while. Now, in this time, there is an empty space in the HOMO, right? There's an empty space here. An electron can use that in order to cross the junction. But when he sees that, he feels this Coulomb repulsion. Because now, when he has to hop into this level, he does not have to have the energy of the original HOMO level, but it has to have that energy shifted up by the quantity U, by this Coulomb binding energy. So the energetics of the junction, of the single particle channels, are changed because of this Coulomb charging energy. I have 5 more minutes. So I will not go through the calculation, of course. Let me just point out that there are 2 things that we don't really know about this junction, which we can use experiments to try to get. And one of them is the rate the electrons can hop from the interface into the molecule and then back out. And then, and this is just a phenomenological description, the rate at which you pump electrons from the HOMO to the LUMO. And this rate depends, of course, on the intensity of the light and the cross-section of the molecule and the angle and so on and so forth. So we don't know these 2 parameters. Okay? But, and then we have machinery to calculate all these kind of things. So if you will come to the tutorial this afternoon, so I will actually explain how we do it. It's not very complicated. So just to give some 2 examples, what you can do analytically, if the system is symmetric, then if U is 0, if there is no Coulomb interaction, then you can get an analytic expression for the conductances. And these, as you can see, do not depend on the rate of optical excitation. So the system doesn't care if we're shining light or not. It's not going to have any difference. So there will not be any photoconductivity in a symmetric junction, and this is an analytical result. So to get some parameters from the experiment, we take the data, we subtract some exponential background because there's always direct tunneling, and we get these distributions. So this is in the dark, under illumination. And from the values of these, you see you have two conductances, and you have two parameters, so you can get these two numbers. And what we get is these two numbers. This is almost 10 inverse nanoseconds. This is the rate of crossing. This is a reasonable number. The number, the rate for exciting electrons from the HOMO to the LUMO is quite small. It's 10 to the minus 3 inverse nanoseconds. And the reason it's small, it actually makes sense. Because this guy has to do with the dipole moment of the molecule. And since the molecule is symmetric, the dipole moment is a small number. So it's very hard to couple electrons to light if there's no dipole. So we kind of understand these numbers. This is just how the molecular orbitals work. And we can actually play a little with the parameters of the molecular junction, because when you have molecular junctions, various parameters change. Here, the only thing that can change are the couplings or the on-site energies, which actually vary when you put a molecule in the junction, and you get, so these are the distributions from experiment, and these curves are numerical distributions. So you see we can learn a lot from this junction just by fitting these parameters. I'm almost done. But what you can really do is get a design principle for photoconducting switches. Because this was the mechanism, remember. You pump an electron from here to here, and then the new electron that will hop in will see this level shifted by amount U. And if you can push this level to be in resonance with the chemical potential, this goes back to one of the first slides, where it showed that you hit the resonance in conductance when you are right at the Fermi level, right? So if you could push this effective level to resonance, then you can get, this is photoconductance, you can get exponentially large increase in the current, as large as you can possibly want. So all we need to do is look for a molecule that has the exciton binding energy as large as the difference between the HOMO and the Fermi level. Unfortunately, nature is playing tricks on us. These are two competing effects. Because in order to get this thing large, right, this is just a Coulomb repulsion between two electrons. So to make it large, you'd want to make the molecule as small as possible, right? Because it kind of goes like 1 over the distance, right? This Coulomb interaction. So you make the molecule smaller, but the direct consequence of making molecules smaller is that you push the levels, you push the HOMO level down and the LUMO level up, right? At roughly 1 over R. So these are two competing levels, and the question of whether there's an optimum, and what is the limiting, what is the optimal thing that you can get in real molecules, we still don't know. So we're actively pursuing this question, but it's hard to know because these calculations tend to be very, very hard. But at least we have a design principle for molecular photoswitches. So I think it's a great time to summary. I showed you 3 types of devices which mimic microelectronic devices and can be made out of single molecules. Negative differential resistance devices, rectifiers, which are just diodes, and photoconductive switches. These are all very, very small devices, and all of them raise new physical questions, which is to me the main source of interest in these systems. I honestly don't care if 20 years